I was asked to give a perspective not of design associated just with basic tensile yield, but some of the other stresses that we've talked about, such as the ultimate stress, shear, and also bearing. Right, so that's what we'll look at here. We've got a simple little lap splice between two plates that's executed by a single bolt, and we've got 7,000 pounds or 7 kips being applied to it. The steel lap joint there, again, one bolt. We've got a failure shear stress in the bolt of 30 ksi is our criterion there. Right, so we're asked first, determine the required bolt diameter here to the nearest quarter inch, which means we're going to design the bolt. We want a minimum factor of safety with respect to shear in the bolt of 2.5. We'll assume that the threads are not in the shear plane. That means that the threads don't go into this little lap connection. The reason why is when you cut the threads, you're removing material. There's stress concentrations and less cross-sectional area. So in this instance, we decide we don't want that issue to have to deal with. So what is the actual factor of safety for the bolt we choose after we do this design? Right. So let's see here. This would be step or part A. And so we're going to deal with, alright, we've got only one bolt, so the shear in the bolt is, there's hardly any analysis to do. It's going to be 7 kips. Now if we had 2 bolts and they're arranged properly, you could assume that each bolt shares an equal amount of the shear, and therefore that would be, if we had 2 of them, that would be 3.5. If you want then a little bit of a small drawing of the bolt, then I'll do that in a slight perspective here. There's the bolt head. It's not a particularly graceful one, drawing that is. But we're looking at shear going across that cross section, and that means that in that cross section is going to be that area of the bolt, and that's just pi d squared of the bolt over 4. Right, and so we're trying to keep then with a factor safety of 2.5 and the failure shear stress of 30, so sigma max can't be any larger than 30 ksi divided by 2.5. Right, we want the maximum to be a lot less than what the criterion is. Maybe we don't feel very confident about that strength of 30 ksi, and that would give us a max stress. Oh, I just saw a critical silly mistake. This is not a normal stress. This is a shear stress, so it ought to be tau, not sigma. I did that on purpose, actually, because that's a common thing to note. It's a communication mistake there, and you want to be careful about that. This is a shear stress, so tau is what we're working with. Right? So that's the max applied shear stress. We want that, the applied, to be less than that allowable of 12 ksi. Since tau is going to be equal to V of the bolt over the area of the bolt, then we can kind of quickly go at this as, alright, we want then, let's see, we've got 7 kips. We're going to divide by pi d squared over 4, and we want that to be less than 12 ksi. Right? And so we'll manipulate that around and we'll solve that for D, and when we do that, right, the 12 is going to go over back onto the left side, d squared is going to go to the other side, 4 comes up on the top, we'll have 28 divided by pi divided by 12, take the square root of that, and I get D equal, that'd be D min would have to be equal to 0.86 inches. Now, how do I know that? Check the units. Kips over kips per square inch. The kips go away, inches squared come up, take the square root, you get inches. Right? They asked us to do this to the nearest quarter, so that means my design value that I'm going to use is 1 inch. Right? Now, when we have 1 inch, what is the actual factor of safety then? So now, tau actual will be equal to the 7 kips divided by pi 1 inch squared divided by the 4, and so we'll get then mathematically 28 divided by pi, or 8.91 ksi, and when we compare that to our criterion of 30, then, oops, nuts. 30 divided by 8.91 is going to be our 3.36 or 7, depending on how you want to round it. So that's where those two different numbers came from. Right? So that's part A. Part B is if the plates are 4 inches wide and 1/4 inches thick, what would be the actual factor of safety if the plates have an ultimate tensile strength of 58 KSI, which would be the case of A36 steel. Yield stress of 36, ultimate of 58. Right? Now, we have to consider two different situations here in B. Are we looking at the stress out here in the main part of the member, or is through fracture through the location of the bolt? And when we're dealing with ultimates, we're really always talking about through the bolt area. Why? Because if I were to do this cut through there, it would be ragged, but I'm going to show it as though it's nice and pristine. You're going to have that little hole showing up there, right? And then out here in this part of the member, that's where we've got our 7 kips. And the stress is now can't be going over that whole area. That's where the bolt is located. Instead, we've got this reduced area, and from the side of that, looking at the edge of the part, then there's your hole, and we're talking about just only that solid area. That's our A, or net area, right? We're told it's 1/4 inch thick, and it's 4 inches total in width, but then we're going to subtract off our bolt, but there's also clearance that's going to happen here, right? So we have clearance to cut the hole, and depending on how we make the hole, we may actually damage it. Depends if it's drilled or punched. If it's punched, we'll damage the area. If it's cut, we won't. So there's an effective larger, there's your hole diameter, 1 1/16, plus the damage that we have there, that's 1 1/8, so 1.125 that we're going to subtract away from the 4. We really only have 2.875 inches that are effective there, times our 0.25 1/4 inch thickness, and so our effective net area is 0.71875 square inches. It's a little too precise, but that's the theoretical net area. So that means our applied stress then equal to P over A. We got 7 kips being applied over our 0.71875 square inches, and so that would be an applied stress of 9.74 KSI in tension. That's much less than the criterion of 58 KSI, so that's good. Our factor of safety then is going to be 58 over that 9.74, and we find out that that is about 5.95, or about 6. Right? Now, if you do it in the gross cross-section, you'll find out you have a factor safety about 8.3, much larger, because of course you're using the gross area out in here, which is just your 4 inches times your 1/4 inch thickness, so 1 square inch. Right? Part C, we're asked to explore the bearing area, right? Bearing of the bolt on the plate, which we just got done talking about this net area. Well, what about the piece that was out to the right, as the bolt is bearing on that part? Right? So you'd have the bearing force, and we have the stress. That's the equal and opposite of what I've got shown here. That's how it goes into equilibrium. And F bearing with just one bolt is the same as the axial force. That's 7 kips. But the area that is in bearing, remember, that's that projected area, and that projected area over that bolt is going to be equal to the diameter of the bolt times the thickness of the part, and that's 1 inch times 1/4 inch, so we have 0.25 square inches. So the stress, the bearing stress, is going to be equal then to 7 kips over the 0.25, which is the same thing as multiplying by 4, so 28 KSI. Our failure stress for bearing was 35 KSI, and that's where then we get then our factor of safety equals strength. Let's see, sigma failure and bearing over our demand. So that's 35 over our 28, and that's where you get 1.25 for your factor of safety for bearing.